All right, after a brief technical delay, our speaker is Ben Knudsen from Northeastern, who will tell us about the topological complexity of pure graph braid groups. Ben?
Thanks, Dan, for the introduction, and thanks for the opportunity to speak in this seminar. Some of you may have been at my last talk in this seminar, where I presented the proof of Farber's conjecture, which ended up not being entirely correct. So I'm happy to have the opportunity to give another talk and correct that error. And fortunately, Andrea Bianchi is not in the audience, so there will be no mistakes this time. Great, so a little bit of background. So if you want to understand how to motion plan on a graph, and that's a very real world kind of thing you might want to do. Maybe the graph is a road and you are motion planning self-driving cars, or the graph is a factory floor and you're motion planning robotic workers. Then one thing you can say about that problem is what is the topological complexity of the graph? Okay, that's not a very hard thing to calculate. But if you are interested in motion planning a lot of different cars or robotic workers on your graph at the same time, and you don't want them to run into each other, then you are instead talking about the topological complexity of the configuration space of some number, k, particles, points, whatever, on your graph. So that configuration space, the definition, is just the space of k tuples of distinct points in whatever background space you're thinking about, and I'm going to be thinking about a graph today. For me, what a graph is it's a CW complex that is finite and has dimension at most 1. So it has edges and it has vertices. It could have self loops. It could have multiple edges, no problem. So there's a graph, and that's a picture of a point in the configuration space of 6 points on that graph. A little bit of terminology. So a vertex of my graph, I'm going to call essential if it has valence at least 3. So these are the graphs, these are the vertices that actually matter. Bivalent vertices don't affect the topological type of the graph, and univalent vertices only affect the topological type up to isotopy equivalence. And so the presence of univalent and bivalent vertices cannot change the homotopy type of the configuration space. So these essential vertices are the only ones that matter from the point of view of studying configuration spaces. And I'm going to write M of gamma for the number of those vertices, the number of actually graphy vertices that we have. Farber's conjecture from 2005 says if you have a connected graph that has at least 2 of these essential vertices, the case where there's one essential vertex is pretty easy to deal with. In that case, it turns out that the configuration space itself has the homotopy type of a graph. And so you can totally understand TC when there's only one essential vertex by studying that graph. So this is not an essential restriction. This is just restricting to the situation where it's not immediate. So you have a connected graph and you have at least 2 essential vertices, then the conjecture says that as long as you have enough people running around on that graph, so enough means at least twice the number of essential vertices, then the topological complexity is equal to twice the number of essential vertices. So this is the meaning of the adjective stable in the title. So stable as in one might think of homological stability. So in the study of configuration spaces, over and over again, things become regular and nice once we increase the number of particles, increase k enough. So it's that sense of stable. So the conjecture is a stable calculation of the topological complexity of the order configuration spaces of essentially an arbitrary graph. What I would like to tell you about is a proof of that conjecture. Are there any questions before I continue. Okay, so I'd first like to try to tell you what is up with this number, twice the number of essential vertices. Why is that a reasonable thing to expect to see here? So for that, I'm going to appeal to a theorem of Tsiolkovsky, which says that as long as you're in this stable range, then actually the configuration space has a smaller dimension than you think it does. It has dimension only number of essential vertices. And that's a dimension, remarkably, that's completely independent of the number of particles once the number of particles is large enough. So this is to be contrasted very strongly with the case of configuration spaces of manifolds, where the homotopy dimension typically grows linearly in the number of points. So in this case, we top out at the dimension. And so this is why Farber's conjecture is a reasonable thing to even think. What it says is that TC is as large as it could possibly be in the stable range. I'll remind you, although this is the topological complexity seminar, so there's no need to remind you that an upper bound for TC is twice the homotopy dimension of your space, as long as you're dealing with a reasonable space. Okay. Questions at this point? Okay. So I'd like to tell you an idea that goes into an approach to this conjecture, which yielded a lot of fruit for a while and then had to be modified. And in order to do that, I'd like to look at an example. So this is the example of two particles on this graph, gamma, which is the cone on 3 points. So if you have two particles on that graph, then something you can do is you can move, or you can start out with them on two of the edges, just pick two of them, and you can move particle number 1 onto the only unoccupied edge by passing through the central vertex, and then you can move particle 2 onto the edge that particle 1 used to be on, again by passing through the central vertex. And that ends you up at a configuration that looks like that, and then you can do it again. And that ends you up at a configuration that looks like that. Oh, I got my updating of my slides in the wrong order. Ignore that last thing that just appeared. And if you do it a third time, you end up back where you started at the same configuration. And if you concatenate those things, then you get a loop in the configuration space of 2 points. And it turns out that that loop is all that is happening. That has all of the information of the configuration space in it. So the configuration space of 2 points in that graph, the cone on 3 points, or the star graph, I might call it, out of habit, is a circle, and the circle is this move where two particles orbit each other by taking turns passing through the central vertex. Questions about this example? This is like the fundamental example, so if there are any questions, it would be a good opportunity to ask. Okay. So the idea then is if you have an essential vertex, then you can choose 3 of the edges, because there are at least 3, valence at least 3. You can choose 3 of them, and then you can produce an embedding of the previous graph, this star graph with 3 edges, into your big graph, and then push forward this circle, which was just a move where 2 particles orbited each other around that essential vertex, and you will get an embedded circle in the configuration space of any number larger than 2 particles, because you can just have the rest of the particles hanging out stationary anywhere you want. Okay. And then if you take the idea slightly more seriously, you will see that if you have a bunch of essential vertices, then you can do this move separately at each of them, right? I can have two particles dancing around near one of the vertices and two more dancing around at another of the vertices, etc. So if I have some number of essential vertices, then I actually get a torus of that dimension, an R-dimensional torus of R is the number of essential vertices. And that is a torus that is embedded inside of the configuration space of any number of particles, at least twice the number of essential vertices I was using. And this torus depends on a bunch of choices, like which essential vertices I chose, which three edges at each essential vertex I chose, maybe some orderings. It depends on, do I have particle 1 and 2 orbit each other at vertex 1 and particle 3 and 4 at vertex 2, or do I have particle 1 and 3 at vertex 1 and particle 2 and 4, right? So there's a lot of choices, but regardless, this is sort of a general thing that you can do. And so Farber's idea is to be interrupted by his cat. Farber's idea is to bound the TC from below using cohomology, which in the classical story about TC is kind of the only game in town. And the way that we're going to use cohomology is we're going to try to detect this torus. So the torus has dimension, if I use all of the essential vertices of the graph, the torus has dimension m of gamma, number of essential vertices. And that's the dimension of the configuration space by Sviakovsky's theorem. And so if we could produce cohomology classes that detected the circle factors of the torus, then we could multiply those together and cook up a long product of zero divisors, and that would be the lower bound on TC that we were looking for. Okay. This is the idea. Are there any questions about the idea? Is it relatively clear? Okay, so this is a good idea. It works. So it works to establish the conjecture for trees. That was Farber's original use of the argument. It suffices with some modifications to establish the conjecture for fully articulated and banana graphs, so-called. That's work of Luke Gateman and Ray Simitar. And with further modification, it suffices to establish the conjecture for all planar graphs. So that was a paper that I wrote, which ended, after correcting the mistake, ended up being what I had actually shown in that paper. Okay. And now there's a problem. If you want to go farther than planar graphs, you run into a problem. And the problem was initially noticed by Andrea Bianchi, and then I thought about it for a while and kind of made precise what exactly was failing. That torus, which is the thing that detects the dimension and whose circle factors we're trying to detect with cohomology, decomposes in homology if and only if the graph is planar. It's equivalent to planarity. So in other words, some circle factor of that torus provably induces zero in homology if the graph is non-planar. And so you just can't run this strategy. You have no hope of running this strategy because there is no cohomology class that detects that circle factor, because that circle factor is zero in homology. So you're stuck. Okay, are there any questions about this train of thought? And so the solution is to forget about cohomology and work at the level of fundamental groups. That's what we're going to do. The thing that makes that a reasonable idea to pursue is this theorem, which I will attribute to these three gentlemen, Abrams, Geist, and Sviakovsky. They all have proven it with various numbers of errors in those proofs. And so I, rather than try to parse out who was the first one to give an error-free proof, I'll just attribute it to all of them. So configuration spaces of graphs are aspherical. No higher homotopy groups. One way that one can prove this is to produce a cubical model that has non-positive curvature, and then there you go. So that's good. So what that says is that if your graph is connected and has an essential vertex, those are the conditions that you need to guarantee that the configuration space itself is connected. Then in that case, your configuration space is a classifying space. It classifies what's called the pure graph braid group of the graph, pk of gamma, by analogy with the braid groups of the plane. And classifying spaces, it has been shown in recent-ish years, have TC that you can understand. So a theorem of Grant, Lupton, and Oprea says that if you have a group, G, and if you have two subgroups, H and K, and the normal closure of H is disjoint from K, and by disjoint, I mean they have trivial intersection, trivial meaning the unit of the group. Of course, two subgroups could not actually be disjoint as sets. So if the normal closure of H is disjoint from K, then, oh, I seem to have lost my, there we go. Then the topological complexity of the classifying space of G is bounded below by the cohomological dimension of the product of H and K. Okay. And I guess I should have probably mentioned earlier, in this talk, I'm going to stick to TC per se. In the paper, the theorem that I prove is actually about higher TC for every value of higher. And what one finds is that the TC sub R, as long as we're in the stable range, K being at least the number of essential vertices, TC sub R of the configuration space is R times M of gamma. And essentially the arguments are all basically the same, just like slightly more complicated to notationally. So I decided not to do that in detail. But maybe one relevant thing to point out is that this theorem has a generalization that's valid for higher TC, due, I think, to Farber and Grant. I hope I'm not getting that wrong. And it's that theorem that makes the argument work for higher TC in paper.
Farber and Oprea. Sorry, I felt the need to. It wasn't me.
Sorry, John. Okay. Any questions about this? So this is the general idea. Forget about cohomology. Work with pi1. We can do that because the configuration spaces are aspherical, and we're going to leverage this disjoint subgroup technology, or hope to do that. And I haven't said at all how we are going to do that. That comes next. But first, questions. Okay. So here's a guess. And this guess comes from thinking about the cohomology argument. The guess is that we should take our subgroup H to be particles 1 and 2 orbiting around essential vertex number 1 in some arbitrary ordering on the essential vertices, particles 3 and 4 orbiting around vertex number 2, and so on. And we should take subgroup K to be kind of almost the same thing, except we change which particles orbit where. So we should have particles 2 and 3 orbiting at the first vertex, 4 and 5 at the second, and so on up to particle 2m and 1 orbiting at the last vertex. This is kind of what you do. Well, no, this is exactly what you do in the cohomology setting. You sort of take cohomology classes that break up these two. These are two different tori inside of the configuration space, you find cohomology classes that detect the circle factors, and then you just sort of make zero divisors out of all of them and multiply them together and see that the result is non-zero. So this is what you would guess if you wanted to, as naively as possible, imitate the cohomology argument in Pi 1. Is the definition clear? What H and K are? Maybe I'll say it again. So when I say H equals this picture, what I mean is this picture is showing you an embedding of an m-dimensional torus into the configuration space. And so H is the image of the fundamental group of that torus. Okay. Okay. So the problem is that, well, now you want to show that the normal closure of H is disjoint from K, and that's not so obvious how to do because the graph braid group is a difficult thing to understand. And so you are contemplating trying to understand what conjugation means in that group. And it's not so obvious. There are presentations of these groups in general available due to Farley and Sabaka. But those presentations are discrete Morse theory presentations that are of the form like generators are critical cells and relations are also critical cells. And so it's like, well, I don't know what that means. So the pure graph braid group is not such a transparent thing to deal with. But fortunately, we can circumvent having to do anything difficult at all with the following observation. So if you have a homomorphism out of a group and its restriction to, it doesn't matter what the target of the homomorphism is. If its restriction to one of the subgroups is injective and its restriction to the other subgroup is trivial, then the normal closure of the one is disjoint from the other. That's because the kernel of a group homomorphism is normal. Right, so this is like a cheater's way to figure out when conjugation doesn't take a subgroup too far. You find a homomorphism that separates the two subgroups. You find a detecting homomorphism. Okay. Are there any questions about any of this before I move on? Okay. So again, our task now is to detect this torus with the homomorphism out at the level of fundamental groups, knowing that it is undetectable in homology. So whatever is going to detect it will have to be slightly subtle because it is not visible in the eyes of homology. So the idea that I will borrow from the work of Gateman and Raciometer, who again established Farber's conjecture in the case of fully articulated graphs and banana graphs. The idea is to use graphs with sinks. So what's a sink? A sink is a vertex of a graph where particles are allowed to collide. So in the configuration space, particles can't collide. But what you can do is you can just declare some of the vertices of your graph to be places where they can. And that's a different topological space. And the virtue of it is that it permits quotient operations between graphs to induce maps at the level of configuration spaces. So I'll illustrate this with this picture. Here's my favorite graph, the cone on 3 points. And if I quotient by the boundary, if I collapse the boundary of that graph to a point, then I get this space, which is the suspension of 3 points. And that map, that projection, definitely does not induce a map between configuration spaces. Because if I had a particle hanging out at one boundary vertex and another particle hanging out at a different boundary vertex, then, well, they would be sent to two particles hanging out at the same vertex, which is not allowed in the configuration space, but it's totally allowed in the configuration space with sinks. Okay. So this quotient map does induce a map between configuration spaces if I declare the image of the boundary to be a sinc vertex. And I'm going to indicate sinc with this green because I don't know, I like poured out the leftover pea soup into the sink. I don't know. So are there any questions about this picture? Okay, and maybe I should say that this is not actually what I do in the paper because it seems simpler to do something slightly different. But this is definitely the idea that led to any progress at all. So I wanted to present it in this way instead. Okay, so here's an exercise. I realize now that I'm actually going quite fast, but that's okay. So here's an exercise. That space, the configuration space of 2 points in this graph with a sinc vertex, has the homotopy type of the wedge of 2 of those graphs equivariantly. And since I'm going fast, we'll talk a little bit through this. So what do? You just hold the graph by the black vertex and let gravity do the work. And what happens when you do that is all the particles fall down into the sink unless they are actually at the top, or maybe one of them is a little bit higher than the other, and then the first one gets to the sink first, and I sort of stop movement, right? So I just expand, I sort of blow air into this graph from the black vertex until there's only one particle that's not at the sink, and then I stop. That's the deformation retract. And there are 2 of them because, well, either it could be particle 1 or it could be particle 2 that is left not at the sink, right? Are there any questions about this picture? Okay. By the way, this is
Actually, sorry.
Oh yeah,
The sigma 2 equivariant. Is the action on the left just like trivial action, or what's?
No, the action. So remember, the
You're
Hoff 2
flipping.
is the ordered configuration space. So there are two particles, and the sigma 2 action is just interchanging those 2 particles.
You're always doing pure here.
Yes,
Yeah,
that's
sorry,
right.
Okay, got it. Yeah.
So actually, no, thank you for that question. It's a very interesting question. What TC is of unordered configuration spaces of graphs, and there's been some work, like especially on trees, but it's very unclear what is happening. It is known that the analog of Farber's conjecture is false. There are counterexamples that were constructed by, I think, Luke and Alessio Mitter. Even I believe counterexamples that are trees. And so yeah, it's a very interesting question. What TC of the unordered configuration space?
That's surprising because in my experience, the pure braid group is way harder than the regular braid group.
Right? Yeah,
Yeah.
it's super weird. Yeah,
okay.
I'm with you. I've spent like basically my entire life working with unordered configurations and like being scared of ordered configurations. And
Yeah.
somehow, yeah, it's weird.
Yeah.
Like it's a little bit. There's a similar situation that's not as radical for TC of configuration spaces of surfaces. It is it seems like what happens is that there's like, well, at least in the case of surfaces, there's enough cohomology around to run a cohomology argument to calculate TC in the ordered case. But that cohomology dies when you go to the unordered case, and so you have to do something at the level of pi1 and work harder. And maybe it's not a good comparison because it's not clear that that's the same problem that happens here, but I don't know. Yeah, this seems to be like a general thing with TC, or a somewhat general thing with TC, where like ordered is easier than unordered in a way that I don't fully understand or like. Okay. But if anyone has as far as I know, there isn't even a conjecture. So yeah, I think Farber is in this room. So if Farber wants to make another conjecture about what TC is in the unordered case, I think that would be super interesting. But as far as I know, there isn't even a guess for a general answer. Okay, so that's an exercise. Here's another exercise. If I look at the following composite, so I have the circle, which is described by the two particles taking turns moving through the central vertex in this configuration space. And I can do this quotient map, which pushes them into the graph with sinks. And then I can mod out by sigma 2. And I can recognize that that has the homotopy type of a wedge of two circles. So now this map is a map from S1 to S1 wedge S1. Like, which one is it? If I look at pi 1, well, what it is it sends a generator to the square of the commutator of two particular generators of this free group. The reason square is that like there's something that happens in the top theta and there's something that happens in the bottom theta, and then when I quotient it by sigma 2, those two become the same thing, and so I actually did them twice. Okay, so that's an exercise that you can just do if you want to. But in particular, well, this is a question for the audience. What's the notable feature of that homomorphism that sends a generator of pi 1 of S1 to the square of the commutator of two generators of that free group?
It's homologically trivial.
It is homologically trivial,
weird.
but it is injective. Okay. Great. So this is the kind of thing that we would like to see. So a corollary is that if you look at this homomorphism, delta, which is the delta that we're looking for, which is induced by this composite. So what I do is I start in the configuration space of twice the number of essential vertices. And I first project onto consecutive pairs of particles. So I project onto particle 1 and 2, particle 3 and 4, particle 5 and 6, etc. And then in each of those factors, I quotient to the, so like, let me back up for a second. How far back do I have to go to see this picture? A ways, that's okay. So what I'm trying to do is I'm trying to detect the subgroup H. So the subgroup H is particles 1 and 2 orbiting around the first essential vertex. I've chosen some ordering. Particle 3 and 4 orbiting around the second essential vertex, and so on. So what I'm going to do to try to detect that subgroup is, well, first I'm going to project down onto those pairs of vertices, and then I'm going to quotient down to the graph with sinks that has the same number of edges as the valence of that vertex, the ith vertex. And the way that I do that is I look at the open star of that vertex and I quotient by everything outside of the open star. And that is going to be a quotient map from the big graph down onto the suspension of valence many particles. And I have the bottom vertex as sink so that this induces a map on configuration spaces. So just to say it one more time, this second map in the ith factor is induced by the quotient map between graphs, which collapses everything outside of the open star of the ith vertex. Okay. So a corollary of that exercise is that this homomorphism is injective after restricting to H. I guess there's like a little bit more that you need to do. You need to also think about the analog of the first exercise when you're looking at a suspension of more than 3 points, but it's the same. It's exactly the same thing. Okay. So it's just a free group with more generators. Okay. Questions about the corollary? I may not have explained it in the most followable way. So I'd be happy to try to clarify. Okay. Corollary of that is that both of these subgroups are actually free abelian of the appropriate dimension, right? They were the image in pi1 of some map from a torus of that dimension. But since we've detected that subgroup, then we now know that actually that was injected to begin with. Okay, so now let's prove the theorem. So remember, what we're trying to do is we are trying to use the lower bound on TC, which comes from the cohomological dimension of the product of two subgroups H and K, provided the normal closure is a disjoint. Okay. Now, each of H and K is free abelian of rank M, and so H times K is free abelian of rank 2M, and the cohomological dimension of that is 2M, which is the thing that is the dimension. So if H and K in fact had disjoint normal closures, then we would be done. So since we already know that delta after restriction to H is injective, it suffices to check that delta after restriction to K is trivial. This is how we were going to show that they had disjoint normal closures. We were going to detect one of them with a homomorphism that was trivial in the other. Okay, so let's try to do that. So this is the map that induces delta on pi1. That was the definition of delta, homomorphism induced by that composite. The subgroup K comes from a product of these spaces mapping into the configuration space, right? K comes from a torus, comes from a product of circles, and those circles are just these spaces. So I have a map from a product of copies of Z to a product of free groups, and I want to show that that's trivial. So that's a map from a direct sum to a product. So if you have a map from a direct sum to a product, homomorphism from a direct sum to a product, and you want to know that's trivial, then it suffices to just check that each of the number of factor times number of factor homomorphisms that you get by inclusion and projection, that each of those is trivial. So in other words, the homomorphism is a matrix, and you want to check that the entries are all trivial. So that's what we're doing. So I'm including one of the factors, which is this circle, the configuration space of 2 points, and it's the jth one. So it's the one that describes particle J and particle 2J and particle 2J plus 1 orbiting at vertex J. So for example, particle 2 and particle 3. Remember, H, which is the one we've already detected with delta, H is the one where particle 1 and 2 are together, particle 3 and 4 are together, etc. K is the one where particle 2 and 3 are together, particle 4 and 5 are together, etc. So there's this offset by 1. Okay, so really what I want to do is I want to show that this composite is null, right? This is like the IJ entry of the matrix that is the homomorphism. Okay. Everybody on board? I may have said that a little fast. I'm not sure. So really what this boils down to is just looking at a particular map from configuration space of 2 points in this suspension of 3 points to the configuration space of 2 points in this graph with sinks, which is the suspension of, sorry, I said suspension earlier when I meant cone, but y'all knew what I meant. Okay, so there are two cases. Maybe I is different from J. So what that's saying is that we're looking at two different essential vertices. Like the sets indexing these products are just the set of essential vertices of the graph. So if we're looking at two different essential vertices, then what this composite does is it puts two particles into the graph orbiting at one vertex, and then collapses everything outside of the open star of a different vertex to the sink. And with the appropriate conventions about like my graph is subdivided enough so like stars are disjoint, blah, blah, blah. That's just constant. That's the constant map to the sink vertex. Okay. Because the movement of those two particles is far away from the vertex that I'm localizing at. Okay. So that's if I is different from J. If I is equal to J, then I'm looking at the same two vertices, right? And now, so I can't get away with something quite so easy, but now the point is that the behavior that we're putting in and the behavior that we're sort of looking for as we map out are different behaviors. So this vertical map has particle 2j and 2j plus 1 orbiting at that vertex. And then I'm following that by projecting onto particles 2j minus 1 and 2j, because I is equal to j. So those two things have only one particle in common, which is particle 2j, right? So maybe it was like 2 and 3, and then I project onto 1 and 2, right? So that map, first I include particle 2j and 2j plus 1 orbiting at that vertex, and then I project onto 2j minus 1 and 2j. Factors as follows. So I project onto the first particle, and then I quotient down onto that graph, and then I include that into the larger suspension. And then the nice thing about configuration spaces of graphs with sinks is that the projections all have sections. That's true in general, but the section is obvious here. You just add the new particle at the sink. And so if I is equal to j, then the composite that we're looking at actually factors like this. Because again, there's only one particle in common between what I'm putting in and what I'm projecting down onto. So whatever particle 2j plus 1 was doing doesn't matter because I'm projecting onto 2i minus 1 and 2i. Okay. So, well, that's good news because that space down there is contractible. And so we've factored our map that we would like to say is null through a contractible space. And so, so that's it. And I am done a little bit early, but I'm going to stop. Thank you.
Thank you, Ben. Any further questions?
Yeah.
Go, Mark.
Do we understand the abelianization of the pure graph braid groups?
Yes, we do. So oh, sorry, you had more to your
I was going to
question.
ask, do we know what these groups look like in the abelianization? The image of your H and K.
Yeah. Right. So I don't know if I can say anything completely general. So in the case of a so in the planar case, they can be chosen No, I think in the planar case, they always inject into the abelianization. In the non-planar case, provably they do not inject into the abelianization. Provably one of the factors is trivial in abelianization. But saying which one it is probably depends on the structure of the graph, like where the non-planarity is located in the graph somehow. Like if you could have vertices that are sort of off on a tree somewhere that you just attached to a K5 or something like that. And then those ones are going to inject into the abelianization, but sort of the ones that are internal to the K5 are maybe not going to inject into the abelianization, if that makes sense.
The reason I asked is because another way to show that the normal closure of H doesn't intersect K would be to show that the images in the abelianization are disjoint. And actually, if you want to, because in the case of braid groups of the plane, the way that Bianchi and Rezio-Mitter get the lower bound is to do something like that. So they get a subgroup of the commutator subgroup of the pure and something else which goes non-trivially in the abelianization. So yeah, and I was kind of wondering about the unordered case. So if you look at your subgroups, surely they're also subgroups of the unordered braid group.
Yes.
But they must have conjugates which intersect there. So if you had a look at like what goes wrong with those subgroups when you put them into the unordered braid group.
That's a good question. I think I probably haven't thought as carefully about that as I should have. Interestingly, in the unordered case, this phenomenon where some of the circle factors are 0 doesn't occur. Instead, what occurs is those circle factors create two torsion in the abelianization, which incidentally, while we're talking about mysteries, is the only torsion that's known in homology for braid ortho.
But can I say so? I think
Yes.
Mark, in the this quotient configuration space, I don't know how you call it, unlabeled configuration space, these two subgroups will be identical. You just because they're different by
Yes.
labels, they will just equal, right?
Yeah, probably. So you need to look for something else. Yeah.
Yeah.
Thank you very much.
Any further questions?
I just want to say, if I may, just very briefly, I mean, I want just to congratulate Ben. I mean, it's a very good work, very interesting, beautiful argument. And despite failures, finally victory, so it's great. Congratulations.
Thank you.
All righty. Thanks again, Ben.
Thanks, Dan.